precipitation reactions is something you're going to do quite a bit. You're going to see it in lecture. You're going to see it in lab. That's coming up. You're going to do a bunch of them in lab. You're going to see it on quizzes. You're going to see it on my exams. I pretty much guarantee you'll see it on the final exam. Okay? So this is something you need to be able to do. And so what these problems look like is most of the time you'll be given two reactants, and you need to be able to predict the products. Okay? We're going to take it one step further in a few slides, but right now all you need to be able to do is to predict the products. So in the video, we talked about how you predict the products in one of these double replacement precipitation reactions. How do you do that? Switch them. We switch partners, then what? Balance them. It's a precipitation reaction. And so we need to take care of these state symbols. So how do you know the state symbols of the products? This, our solubility table. And so you're going to switch the ions. So it's a double replacement reaction. So you're going to switch partners, and you're going to have two new compounds on your product side. One at a time, you need to look at your solubility table to figure out whether they are soluble or insoluble. Soluble means that they are dissolved, they will dissolve in water. Insoluble means they will not. So, the reaction is happening in water. Both of your reactants are aqueous, means they're both dissolved in water. And so if you make something in water that can dissolve in water, it immediately is dissolved in water. And so that will be aqueous. But if you make something that is not soluble in water, it will become a solid. And so here, what we have is a beaker, and then in the beaker was one solution, something dissolved in water. Up here, we had another clear solution, something dissolved in water. When we poured them together, we made two new products, okay? So let's say that what was in the beaker was this lead nitrate. When we poured this in, this was potassium iodide. We're going to switch partners. If we switch partners, what two new ionic compounds did we make? Lead iodide. We made lead iodide and what? Potassium nitrate. So we have to figure out whether these are soluble in water. It can be that they both are, neither are, or one is. So you have to look at each one. Yes?
How do you know the subscripts are?
Based on our ion charges. Just like when we made ion compounds before. So lead is a 2 positive charge, so that came down here. You're going to completely ignore the subscripts over here.
Okay.
You're going to have to group balance it after you make this. The subscripts here are determined solely based on the charges, not what was on the reactant side.
All right.
So we've made these. We have to come back and look at our table. And so the way the table is written is they make generalizations and then give exceptions to the generalizations. So let's start with lead iodide. Look up there and see if you can figure out how to read that to find out if lead iodide is soluble or insoluble. Why is it insoluble? Right. It says iodide is soluble except when it is with lead. So that is an exception. So lead iodide is not soluble, and so it is a solid. Now we look at potassium nitrate. Soluble or insoluble? Soluble, and how do you know? Right. Potassium, it says, is soluble with no exceptions, And then nitrates are soluble with no exceptions. And so clearly this one is soluble. And so we have to put aqueous. We have to put these state symbols. If you don't put them, you are wrong. Okay?
Like the units.
Just like units, yes. And so here, we wrote it out and we balanced it. You can balance it before or after you do the state symbols, it doesn't matter. The state symbols don't affect the balancing whatsoever. So my suggestion is to do the state symbols and then balance it, because you're probably more likely to forget to write state symbols than you are to forget the balance. But either way will work. So here is another one. This one is written out in Word form for you. So you need to read through that and figure out what the reactants are, and then what products are you going to make. And down here at the bottom, they've already pulled the reactants out for you. We're going to do this whole thing from beginning to end, so I'm going to copy that up here. So it says we're going to mix these two things, cadmium nitrate and sodium sulfide. And when you do that, you get an orange precipitate. The precipitate is the solid in a precipitation reaction. It precipitates to the bottom of your beaker. Okay? So first thing we need to do is, it says identify the precipitate and write the balanced chemical equation. So to find the precipitate, we first have to find both of the new products. Because once we have both new products, then we can figure out whether they're soluble or insoluble. The insoluble one will be our precipitate. So if we switch partners here, what is one of the compounds we're going to make? Cadmium sulfide. That's CdS. We don't know what the state is yet. And what is the other one we're going to make?
Sodium nitrate.
Sodium nitrate. It doesn't matter which one you put first or second, whichever one you want to do. So now we can go back to our table and figure out whether they are soluble or insoluble. Is cadmium sulfide soluble or insoluble? Nobody's quite sure. It is up there, what you're looking for. Why are you going to say insoluble?
Sulfides are insoluble.
Correct. Sulfides are insoluble except when they are with ammonium or a group 1 metal. Is cadmium a group 1 metal? No. And so it is insoluble. So we're going to put solid. What about sodium nitrate? Soluble. It says, just like with potassium, sodium is always soluble, and again, nitrate is always soluble. So this is aqueous. Now, we learn, we live in the real world. I know you're in here to get a good grade, not necessarily, hopefully though, but not necessarily to learn. With good test-taking strategy, how could you have known which one was the solid simply based on the question? Known as cadmium orange. Which of these two things do you think is known as cadmium orange? The one that has cadmium in it. Okay. Sometimes there's a shortcut in the question that can help you out. Also, that's going to help you confirm that you did this right. If you found that this one was insoluble and that one was soluble, but the pigment's known as cadmium orange, hopefully that sends alarm bells going off in your head that something might be off. So now we've got our state symbols. What's the last thing we have to do? Balance it. Is it balanced? No. Why not? I'm missing a 2. I have 2 nitrates over here, I have 2 sodiums over here, I only have 1 of each over here.
Put a 2 on the right side.
I can put a 2 here to fix both of those. Cadmium and sulfide were balanced to begin with. So now I am balanced. That is a complete precipitation reaction. It's balanced and I have state symbols. There are the steps that we went through. So here is another one. We have barium chloride and sodium chromate. What are we going to make when we switch partners? Barium chromate.
Sodium chloride.
Plus sodium chloride. You know sodium chloride is soluble in water. If you went back, the table would confirm that. I'm just going to put aqueous there off to begin with. We'll go back. Barium chromate. So this actually does not tell you. So let's go back to the problem and see if we can figure it out. Can you tell, based on the problem, whether barium chromate is soluble or insoluble?
This is a precipitate form.
Right. It says, given that a precipitate forms in this reaction, that means one of the 2 products has to be a solid. And you certainly know that it's not sodium chloride. And so barium chromate must be a solid. Okay. Sometimes you're going to do this. You're going to switch partners. You're going to get 2 products, and they're both going to be aqueous. If both are aqueous, in reality, no reaction happens. You would put yields, no reaction, or NR. If you put yields and they're both aqueous, that is incorrect. Let's think about it. If you dissolve an ionic compound in water, what happens to the ions?
They break apart.
They break apart. That's why they can react here, because they're just floating around independent of each other, and so they just happen to run into each other, and sometimes they react, sometimes they don't. But if you make a product that is aqueous, it's broken apart also. And so in reality, you can't tell the difference between the reactants and the products because they're just broken up into ions. And so you put your reactants together, they're floating around, and nothing ever changes. And so that is no reaction. So we made our products, we figured out the state symbols, then we have to balance it. Put a 2 on the sodium chloride, that balances the sodium and the chloride. Yes?
So we do have the solubility table.
It is on the cheat sheet. Yes. It is on the cheat sheet.
Imagine trying to remember that.
No. I don't think you ever, I never took a class where you had to know that.
I imagine a chemist might.
But just based on using it, you get familiar with it. But I never took a class where I had to have it memorized. I always had it front and center on my folder, like so I could refer to it a lot.
Yeah.
So we're going to talk a little bit more about acids and bases. We already talked about them briefly once. We still have an entire lecture on them coming up. So here we're just going to talk about them simply because an acid-base reaction is actually a type of a double replacement reaction. And so we said acids and bases react because acids make H plus ions and bases make OH ions, and H plus OH gives us water. So this really is a double replacement reaction. So here's an example of an acid, hydrochloric acid. It's an ionic compound. So it's going to break up into hydrogen ion and chloride ion. Here's a base, sodium ion and hydroxide ion. So all those ions are flying around. When the H plus hits the hydroxide, they're going to react. And it makes water, which is a liquid. It's liquid water. And so it's very similar to a precipitation reaction. But in this case, you are making the water that everything is dissolved in. And the other thing you're going to make is salt. And so here it's sodium chloride, and it is what we consider salt. But for an acid and base reaction, you will always make water and a salt. In chemistry, the term salt is used for ionic compounds. An ionic compound that is soluble in water. And so, you're going to make water and a salt with an acid-base reaction. It is a double replacement reaction, just like our precipitation reactions. You're just making water as one of your products instead of a solid. We have one more type of reaction, and that is a combustion reaction. That was not on our list of 4 reactants. It doesn't really fit into any of them. In some cases, it's kind of like a decomposition reaction. In some cases, it's kind of like a synthesis reaction. It kind of really is its own thing. If you burn something, sometimes you're going to make something bigger, sometimes you're going to make something smaller. So think about when we put that magnesium in our flame a few weeks ago. Remember when it burned bright like that? What do you think we made there? We're going to do that exact reaction again, I think, next week. That's the postlight that Derek was working on. So what do you think we made when we burned magnesium with oxygen? Can you break magnesium down into anything smaller? No. So you can't break it down.
Magnesium oxide?
We made magnesium oxide, yes. We took the magnesium, it reacted with the oxygen in the air to become magnesium oxide. But if we take a cardboard box and we burn that cardboard box, do you think we're making things that are more complicated or less complicated than whatever makes up cardboard? Less. We're breaking it down into very simple compounds, right? And you get carbon dioxide and water vapor and all kinds of hazardous chemicals coming off of that cardboard box, right? And so sometimes it gets more complicated. It's more kind of like a synthesis reaction. In other cases, it gets smaller. So really, combustion is its own thing. This is our methane burning. And so we're taking methane, reacting with oxygen, and we're going to get carbon dioxide and water. If you burn anything that's made up solely of carbon and hydrogen, you're going to get water and carbon dioxide as your products. That's not something you have to know, but that may help you at some point. For the most part, if something is made up of carbon and hydrogen, you're going to get water and carbon dioxide as your products. This is assuming 100% combustion. If any of you are engineers, or if you work with engines or anything, you know that getting efficiency out of your engine is a big thing. The gasoline that goes into your car is pretty much only carbon, and hydrogen. So in a perfect world, all that you would get out is water and carbon dioxide. But there are other things in there, like carbon monoxide and other compounds. That's because the burning in the engine isn't completely efficient. If you have a theoretical situation where it's 100% efficient, you'll get only water and carbon dioxide. So we're going to go through, and there's several slides, I don't remember exactly how many, there's quite a few. And we're going to look at different reactions, and you need to tell me which type of a reaction it is. And this is going to help you in several ways. And some questions will be just like this. What type of a reaction is it? Other type of questions, they'll give you products, they'll give you reactants, and ask you to predict the products. And if you don't know what type of a reaction it is, you don't know how to predict the products. So you need to be able to look at the reactants to figure out what type of reaction it is. So on this slide we have reactants and products. And this is our generic version with our spheres, and then there's an example down below. The first one, what type of a reaction is that? Decomposition. How did you know it was decomposition? It broke apart. There was one reactant. That is your key for a decomposition reaction. There is one reactant. And we said that I cannot ask you to predict products from a decomposition reaction. It's just too complicated. It's something you really have to do in the lab to figure out what it's going to turn into. What about this one? What is this one?
Synthesis.
How did you know that was synthesis? You're making one product. So again, I won't ask you to predict the product to a synthesis reaction, although this one is fairly simple. You're combining zinc and chloride. You're going to make zinc chloride. There's nothing else you can make. And zinc chloride has to have specific subscripts based on the charges. If you have something that's not, if you're making a molecular compound, then you can make anything you want. And then there's absolutely no way you can predict that. What about this one? What is this? How do you know it's single displacement?
Because there's only one product and then you have an extra element.
Well, they're both products.
A and C switch.
A and C switched, yes. So really what you're looking at, what I want you to pick out of this that tells you it's a single displacement is your reactants are an element and an aqueous compound. You have an element and an aqueous compound, and they didn't simply just come together in a synthesis reaction. Because you have two products, and so it cannot be a synthesis reaction. And so the only other thing these two things can do is a single displacement reaction. What about the last one? It's double displacement. The keys are your reactants are two aqueous solutions, and then you made two new ionic compounds. These two didn't just come together to make one gigantic product. Something more complicated happened. Here you can see that they just simply switched, but even if you couldn't, if you know that you started with two compounds and you ended with two compounds, double displacement is the only thing that could have happened. So what about this one? What is this one?
Synthesis.
Synthesis is one product. What about number two?
No, that's a double displacement.
It's double displacement. We're starting with two aqueous compounds and making two ionic compounds. We just switched partners. What about number three?
Decomposition.
Decomposition. We have one reactant. What about number four? Single displacement. We have an element and a compound. So that in itself should be enough to tell you it's single. But if you really look at it, the calcium replaced the lead. Now the lead's by itself and the calcium is in the compound. That is a single replacement reaction. Now it gets a little bit tougher. Because now all we have are pictures. What do you think is going on in A?
Double displacement,
How do you know it's double displacement?
because you have two precipitates.
Well, we had double displacement up here where there was only one.
But you have two solids.
Right. And so this is a double displacement. This is a precipitation reaction. It's just in this case, both of the products are solids. One of them is a yellow solid. One of them is a purple solid. So we had a solution down here. We're dripping in another solution, and we're making two new products, both of which are solids. What about B? Combustion. How do you know? Fire, right? If it's fire, that's combustion. Also, what do you think this is? That's magnesium. That's exactly what we did. That was a combustion reaction. C is a little tougher. Does anybody know what's going on? What if I tell you that this thing is a pH meter? Does that help?
Double displacement.
It's double displacement. How do you know? What is a pH meter used for? Acids and bases. So this is an acid-base reaction, and we said acid-base reactions were a type of double displacement reaction. C or D is harder to see. It's clear up here. I don't know, you probably can't see it. But what we have is there's a beaker. In the bottom of the beaker is a bubbling green liquid, and then sitting in that is a chunk of metal. So what do you think that is? What type of a reaction is that? Think about what your reactants are. What do you think your reactants are?
Single displacement.
Why do you think it's single?
Because if it's a metal, it's one element.
If you have a metal, it's one element. Yes. And so then we don't know what's in that liquid. And so you could argue, since we don't know what's in the liquid and we don't know what the products are, it could be a synthesis. You could just be taking the two things and putting them together. But this is a single displacement reaction. This started with a chunk of metal, which is one element, and then an ionic compound dissolved in water down here. Once you put the metal in that, the metal element is kicking out one of the elements in the compound that's dissolved in the water and causing a single displacement reaction. Yes?
You call that oxidation, or is that something else?
That is something else. So we're coming to that. What about E? What do you think that is?
I don't even know what the picture is showing.
So, okay. You know, it never occurred to me.
It looks like a tree.
It's like ice.
See, I've done enough of these. I look at that and I immediately know what I'm looking at. It never occurred to me that someone would look at that picture and not immediately know what they were looking at.
Yeah.
So what this is, there's a test tube right there. Then there's a clear liquid. And then there is white, fluffy solid coming down from the top and settling at the bottom.
Is it like salt?
Some kind of non-metal, I guess.
What type of reaction is this? It's double. And so up here you saw the drops going in. The drops are already in. And so the drops hit the top of the water here, formed a precipitate, a solid, that is now sinking down to the bottom of the test tube. You're gonna do a number of these in the lab. What about this one? That's combustion. C, to this day, I have no idea what's going on there. I really do not know. So we're gonna skip that. What about H? What we have here, there's a beaker with a liquid in it, and then down at the bottom, there's a chunk of something, and then bubbles coming off.
What is he?
I got a lot of guesses with your voices going up at the end.
Single displacement.
It's single. Yes. You said single, right? Yes. And he said it without his voice going up at the end. So what this is just water, and then this is an element. I would guess calcium. It's a metal, usually probably something from group 1 or 2, that's in there and it's reacting. And so let's say it's calcium, and then we have water. Coming up, in some cases, is going to help you think of water not as H2O, but as HOH. Because remember, we said with acid and base, you make water when you take an H ion and an OH ion. And so you can also think of water as an ionic compound made up of a hydrogen ion and an OH ion. So what's happening here is the calcium is kicking out that hydrogen to make calcium hydroxide, and then you're going to get hydrogen gas. So those are the bubbles that are coming off. So that is a single displacement, but kind of like this one, because you don't know exactly what it is you're dealing with in terms of reactants or products, you could make a case saying it could be synthesis. Because that could be combining with whatever is in here to make a bigger molecule that is a gas. You don't know for certain, but it is a single displacement reaction. What about this? What is this one? How do you know it's synthesis?
You have one product.
One product. What about this one? Decomposition. There's one reactant.
Single displacement.
Single displacement, yeah. So the blue kicked out one of the green ones to make a blue-green, and now the green ones floating around by themselves. And so, if you're paying attention, what does this one must be? Because of course you're going to have one of each one. So this one is double displacement. What's this one? Synthesis. There is one product. We're going to now come back to our precipitation reactions, and we're going to make them more complicated. Yay. This is not hard. This is just a lot of grunt work. You're going to have to write a whole bunch of stuff, and if you don't write a whole bunch of stuff, I am going to mark part of it wrong. And I hate these just as much as you, because if you have to write a whole bunch of stuff, I have to grade a whole bunch of stuff, okay? But these are important, and you're going to have to do this. And so for our precipitation reactions, we can simplify them. Because we said if you make two products and they're both aqueous, it's like nothing ever happened. But for the reactions that we saw, such as this one, where we get one solid and one aqueous, that aqueous one is dissolved. And so they're broken apart. So we don't really have sodium nitrate. We just still have sodium and nitrate ions flying around that didn't do anything. And so this isn't really a part of the reaction because it didn't do anything. It's just the leftovers. And so what we're going to do is we're going to take this reaction, we're going to simplify it down to just show the parts that did react. And so what we wrote previously is called the molecular equation. It shows everything in molecule form, not as broken down into ions. So this is the molecular equation. But we know that they are, in fact, ions, though. We're not reacting sodium nitrate with sodium chloride. We're reacting silver ion, nitrate ion, sodium ion, and chloride ion. They're all floating around independently. So the first thing we're going to make is what we call the ionic equation. This is also called the total ionic equation. In order to make the ionic equation, we take everything that is aqueous, whether it's a reactant or a product, and break it apart into ions. So if we go back, that, and that are all aqueous. So if we break that apart, we're going to get a silver ion and a nitrate ion. A sodium ion, a chloride ion, a sodium ion, and a nitrate ion. That is a solid. It does not break apart. Something that is a solid, a liquid, or a gas does not break apart. You only break it apart if it is aqueous. So here we've done that. Everything that was aqueous is broken apart. They now have charges because they're ions, and they all have to stay aqueous. If you leave all these little aqueuses off, I'm going to mark them wrong. If you leave one of them off, I'm going to mark it wrong. Silver chloride was a solid, and so it did not get broken apart. So what we have are, we have 4 ions on the left. On the right, we have a compound and 2 ions. We have sodium and nitrate floating around on their own on both the left and the right. We call those spectator ions because they did not react. The silver and the chloride reacted. The sodium and the nitrate didn't. They were spectators. They watched the reaction occur. And so we're going to get rid of those. So in this case, the sodium and the nitrate are on both sides. So we're going to cross them out. And whatever we don't cross out, we write down below. And this is called the net ionic equation. So we had the molecular equation. We used that to write the total ionic equation. We crossed out the spectator ions. And what is left is the net ionic equation. And the net ionic equation simply tells you what the reaction was that occurred. Silver ion reacted with chloride ion to make silver chloride solid. That is what happened. The sodium and the nitrate had no role in this whatsoever, so this is the only part that is important. So let's do an example. Anybody in radiology? Has anyone had one of these barium enemas before? It's an enema, but you swallow it. It comes from the top. And so what this is, it's a contrast dye. You drink this, and it goes into your intestines, your digestive tract. They take an X-ray, and then it will absorb the X-rays, and so it shows up as white on your X-ray. It shows up as white on your X-ray, which allows you to see things you wouldn't normally see in an X-ray. You can see the folds of the intestine here. You would never ever see that in just a plain X-ray. So it says,
Like in a CAT scan where they give you stuff for your IVs, so.
I'm not as familiar with a CAT scan. I think CAT scan is something else. CAT scan. So it says the white stuff is barium sulfate. And you can make this by mixing barium chloride and sodium sulfate. The question asks us to write balanced, molecular, ionic, and net ionic equations for this reaction. So the first thing we have to do is write our reactants. So we have barium chloride. What is the formula for barium chloride? BaCl2. And we're mixing them. This is a precipitation reaction, so we know our reactants are going to be aqueous. So I am going to say this is aqueous. And then we have sodium sulfate. What's the formula for sodium sulfate? Na2SO4. Sulfate has a 2 negative charge. H2SO4 aqueous. If we switch partners, double displacement reaction, what is one of the things we're going to make? Barium sulfate. What is the formula for barium sulfate?
BaSO4.
BaSO4. Barium is a 2 positive charge, so sulfate is a 2 negative charge. We have BaSO4. We don't know the state yet, but we'll come back to that. What's the other thing we make? Sodium chloride, which we know is aqueous. So I think you're all comfortable using the solubility charts. We're not going to go all the way back to it. I will tell you barium sulfate is insoluble. So I'm going to put solid there. My suggestion is to balance it at this point. If you balance it at this point, and then you just keep that balance as you move on, the total and the net ionic equations will stay balanced. If you get to the end, and then you balance, you actually take some thought and work to go backwards. Balance now, and then carry it forward. So, what is out of balance? Sodium and the chloride. All I have to do is add a 2 here. So next thing I'm going to do is I'm going to write my total ionic equation. So I need to go through and break apart everything that is aqueous. So I have barium chloride, so I am going to get barium I'm going to get barium chloride plus sodium that is a solid, so I'm not going to break it apart, but I still have to copy it down. Does that look correct?
There's 2 chloride.
Correct. I purposely skipped numbers. And so when we dissolve barium chloride, we get 2 chlorides out of that. There are 2 chlorines, and so we are going to get 2 chlorides. Now they are chlorides. That is what we are counting, and there are 2 of them. And so that 2 has to be a coefficient. This 2 became a coefficient 2. You cannot put that 2 down there because Cl2 with a negative charge doesn't exist. That is not a thing. Here we had 2 sodiums. So I need a 2 there. Over here, I had 2 sodium chlorides. Each sodium chloride gives me 1 sodium, but I had 2 of them. And so I have 2 of these, and I also have 2 chlorides. That 2 went to the sodium and the chloride. Because this was balanced, as long as I carry that down, this is balanced also. I have 1 barium, I have a barium. I have 2 chlorides, 2 chlorides, 2 sodiums, 1 sulfate, 1 sulfate. Next thing I have to do is I write my net ionic equation. To get there, I have to cross out my spectator ions. What are my spectator ions?
Sodium and chloride.
The sodium and the chloride. So I'm going to cross them out. Because there's 2 on both sides, I'm going to cross out the 2 as well. And then that is it. The barium and the sulfate are not spectator ions. Yes, there's barium on both sides, but here it's in a compound. So really what I have is I have barium ion, and then I have barium in a compound. And those are not the same thing, and so they do not cross out. So all I have to do is whatever is not crossed out, write down below. And that is molecular, total ionic, and net ionic equations. What I see people get wrong doing this is they don't carry that 2 to the chlorine. They will carry it to the sodium, but they won't carry it to the chlorine. They'll forget about that 2 becoming a coefficient. They'll leave the 2 down here. A lot of times they'll break apart a solid when they shouldn't. You only break apart things that are aqueous. And I'll also see people that when they break apart something like the sodium, they'll break it into sodium, sulfur, and oxygen. Sulfate, remember, is a polyatomic ion. It is going to stay sulfate. That is locked in place. The sulfate as a whole will move around and change partners, but the sulfate itself will not break apart. That's what we did. Okay. We're going to do quite a few of these in the lab. I think it's probably in 2 weeks. It's not complicated, but you have to do all of the work. If you want me to look at some of these, if you want to go home, do them on a piece of paper, do them on Word, on Paint, whatever you want to do, and send me the whole thing, and I would be happy to go through and look at all the details for you, so that you know that you've got everything correct. Because there really are a lot of details that go into that. What to break apart, all of the state symbols, all of the charges. When you break it apart, you have to add the charges. You have to balance everything. Take subscripts, make them coefficients, everything. I'd be happy to look at that for you. Questions? Questions on this before we move on to something a little bit different?
Is there there's practice questions?
In the homework.
The homework.
The homework. I would imagine, has anybody done their Canvas homework yet this week? I would imagine the written question in the Canvas this week. Just happened.
Oh, it's back. Yeah.
Nope, the written question is an empirical formula. But there is one here. And if you just search online for precipitation reactions, you will find enough to last you the rest of your life. And there is no precipitation reaction that would be not what we're covering. If you see precipitation reactions, go for it. Okay, so next thing we're going to talk about is energy in reactions. We have another lecture coming up, I think it's in 2 weeks, where we talk more about energy. But right now we're going to talk about energy in terms of a reaction in sort of a superficial way. So every time you have a reaction, there is going to be an energy change. When you burn methane, obviously there's something going on with the energy there, because it is very hot, right? In this case, the energy is being released from the reaction. It is being used, it's coming out of the reaction to cook your food or cook your arm if you reach over your Bunsen burner, right? It's cooking something, it's making something very hot. The energy is coming out of the reaction into something else. And so that other thing is going to get hot. All changes, whether they be chemical changes or physical changes, are accompanied by energy changes. So if I take a piece of paper and I rip it in half, it's a physical change, right? But I have to put energy into that to rip it. Every change has an energy change that goes with it. So we're going to draw these energy diagrams. What this energy diagram is, it's a simple graph. We have x and y axes, and then we're going to draw a line showing the amount of energy in our reactants and products. On the x-axis, we have time. As you go from left to right, time is going forward. This is the beginning of the reaction. That's the end of the reaction on the right. The y-axis is how much energy is in the ingredients of our reaction. As you go up, there's more energy. So in this reaction, do you think we are absorbing or releasing energy from our reaction? We're two very confident answers. Do we end up with more or less than we started? We end up with less than what we started, and so we released energy. We lost energy, we released energy. That is called an exothermic reaction. Think exit. The energy is exiting the reaction. Over here, we have the opposite. That is called an endothermic reaction. I don't have a good way to remember endo. But endothermic reactions take in energy. So in this case, we started with our reactants, we gained energy, our products have more energy than our reactants. That idea is fairly simple. Second question is, what happens to the temperature of the surroundings? If you have an exothermic reaction, it's going on in a beaker. You touch it. It's going to be hot or cold? It's going to be hot. Even though it is losing energy. People like to think, well, it's losing energy. It's going to feel cold, right? It has less energy. But your hand is not the reaction. Your hand is the surroundings. The reaction is losing energy. That energy has to go somewhere. It's going to go into your hand. So your hand gets hot. An endothermic reaction takes in energy. It's easy to say, well, it has more energy now, it must be hot. But it's going to feel cold because your hands are the surroundings. If it's taking in energy, it has to get that energy from somewhere, from your hand. So the reaction gains energy, but your hand loses energy. Same thing with a thermometer. If you put a thermometer into a reaction, the thermometer is the surroundings. It's either energy is going to come out of the reaction into the thermometer, making the temperature go up, or the reaction is going to pull energy out of the thermometer, making the temperature in the thermometer go down. So it can seem a little bit backwards. You have to think it through completely. What might help you is to remember exothermic reaction. What's the best example of an exothermic reaction, something that gives off energy that you can think of? Burning something. Is burning something, does that feel hot or cold?
Hot.
Hot. Burning is exothermic. Burning feels hot, so exothermic must feel hot. Right? If you burn something, a thermometer is going to go up. And if you know that burning is exothermic, an exothermic reaction must make the temperature go up. Okay? Most reactions are exothermic. And there's a reason for that, and we'll learn more about that when we really cover this. But the majority of reactions are exothermic, meaning they release energy. Fire is one of them. Here we have burning hydrogen gas. Down here we have the fire from our Bunsen burners. Most acid-base reactions are also going to give off heat. If you mix hydrochloric acid and sodium hydroxide, yes, you're going to get a reaction, but it's also going to feel hot. If you go home and you mix a bunch of vinegar and baking soda, you're going to get a whole bunch of bubbles, but if you felt it, it's probably going to feel warmer than room temperature where the two started. Some of them, though, are endothermic. Can you give an example, other than burning, of an exothermic reaction from real life?
Electricity?
Fever is good. I'm not sure you know how good it is, but it's very good. Where does the heat from a fever come from?
Your blood?
Your muscles.
Your muscles, but why do your muscles give off?
Because they feel trapped.
You're metabolizing things, right? You're taking the things in, you're digesting them, you're metabolizing things. That gives off energy. That's why your body does that, to get the energy out of it. Your body needs energy to do things. If I step over here, my muscles did that, but my muscles needed energy to move me over here. So metabolism is a very good example of an exothermic reaction. How many people have ever sprained their ankle? Did you put hot or cold on it, or both? Maybe I'll save this example. How many people have been camping? You ever been camping when it was cold? What did you do to help stay warm? What, particularly your hands? You got gloves. Fire. I'm not getting what I'm going.
Hand warmers?
Hand warmers, yes, thank you. Hand warmers are an exothermic reaction. How many people have used one of those hand warmers? What do you do when you take it out of the package? You shake it. Sometimes you have to squeeze it. There's like a little package in there, right? You squeeze that package to break it, and then you mix it. That's an exothermic reaction. You have two reactants. One of them is in a package, though, so they're not touching each other. You break that packet in there. Now they're touching each other. They react. They give off heat. You've seen the glow sticks, right? It's the same idea. It's still giving off energy, but instead of heat, it's light. And what do you do to activate a glow stick? You break it, right? There's that glass vial in there. When you break it, the contents of the glass vial mix with the liquid outside the glass vial, and you get light. What about endothermic? Ice pack, the instant cold packs, right? It's the same idea. There's two ingredients. They look exactly the same. It's the same idea. You break the packet inside, two things mix, it gets cold. Because it's endothermic, it's absorbing heat, it's going to take the heat out of your ankle. You're going to make your ankle cold, which should help with swelling. Now, last thing we're going to talk about today, oxidation reduction reactions. Now, we were talking about this before class. In oxidation reduction reactions can be very complicated. We could spend an entire 3-hour lecture on oxidation reduction reactions and not cover it all. We are not going to go nearly that in depth. We're going to just touch the surface of oxidation reduction reactions. Oxidation reduction reactions are much more complicated than the other types of reactions we talked about. And so for a chemist, they can be a very good tool to use because you can do some fancy things with them. But you are not chemists. You're learning chemistry to apply to your field. For a lot of you, that is a health field. If you're dealing with chemistry in the health field, you're not dealing high-level chemistry. You need to know what's happening with your patient, right? You need to know why you're giving them this drug, why you're giving them this IV, and how not to kill them. And so we're going to cover oxidation reduction reactions deep enough